Now we'll talk about Seebeck effect. What is the Seebeck effect? It's a phenomenon in which a temperature difference between two dissimilar electrical conductors or semiconductors produce a voltage difference between the two substances. That's referred to as Seebeck effect. You are able to see a difference in temperature in a metal or material will induce the electric current. In 1821, the German physicist Thomas Johann Seebeck discovered that in a circuit consisting of two dissimilar metals like iron and copper, an electromagnetic force is developed when the junctions are maintained at different temperature. That's referred to as Seebeck effect. Two dissimilar metals contains to form two junctions, and this is called a thermocouple. This is a thermocouple. The electromagnetic force developed in this circuit is referred to as thermoelectric EMF. The current passed is referred to as thermoelectric current, and this effect is called a thermoelectric effect or Seebeck effect. So there is an implementation for Seebeck effect. You are able to see you got a hot junction here and you got a cold junction here. If the hot and cold junctions are interchanged, the direction of current will be reversed. So Seebeck effect is reversible. In a copper and iron thermocouple, the direction of current is from copper to iron at the hot junction. The magnitude and sign of thermo EMF, that's electromotive force, depends on the material of two conductors and the temperature of hot and cold junction. Seebeck, after studying the thermoelectric properties of different pairs of metals, arranged them in a thermoelectric series. The series formed, or the metals which is placed based on their thermoelectric properties, as referred to as thermoelectric series. The direction of current at the hot junction is from the metal occurring earlier in the series to the one occurring later in the series. The magnitude of a thermo EMF is larger for metals appearing farther apart in the series. Here is the thermoelectric series of the metals. It's bismuth, nickel, palladium, platinum, copper, manganese, mercury, lead, tin. It's gold, silver, zinc, cadmium, iron and antimony. The position of the metal in the series depends upon the temperature. The thermo EMF of any thermocouple has a temperature dependence and is given the relation as V equal to alpha into theta plus half into beta into theta square. But theta is the temperature between the junctions and alpha and beta are constants and depends on the nature of the materials. Now we'll talk about the neutral and inversion temperature. The graph showing the variation of thermo EMF with the temperature of the hot junction taking the temperature of the cold junction, it's theta c here as origin. For small difference in temperature between the junctions, the graph is a straight line. For larger difference at the temperature, the graph is a parabola. Keeping the temperature of the cold junction constant, the temperature of the hot junction is gradually increased. The thermo EMF rises to a maximum at a temperature theta n, that's your neutral temperature, and then gradually increase up to theta n, that's neutral temperature, and it started decreases and eventually it will become 0 at a temperature that's the temperature of inversion. Beyond the temperature of inversion, the thermo EMF changes signs and then increases. For a given thermocouple, the neutral temperature is a constant, but the temperature of inversion depends on the temperature of cold junction, and these temperatures are related through the formulation is here. So temperature of cold junction plus inversion temperature divided by 2 is equal to the neutral temperature. So theta C is the cold junction, theta n is the neutral junction, and theta I is the inversion temperature.